Right. Good afternoon. Welcome to MSE 245 presentations this April 20, 2022. This is in line with the course goal, which is to understand semicon characterization techniques. Here are the given instruction and guidelines for these second individual reports. This second individual report will cover topics in physical and chemical characterization of semiconductor materials and devices. What are the suitable topics? Number one, special technique related to X-rays, such as X-ray photoelectron spectroscopy or XPS and X-ray topography. Another is a special technique related to ion beams, such as TOF-SIMS and Rutherford backscattering. And last but not least, a new development in electron microscopy, such as electron backscattered diffraction. So the format will be as a PowerPoint presentation. The presentations must include basic concepts to understand the technique, at the very least as discussed in the main textbook. The student must report at least one recent paper. All references should be properly cited. The students should actively search for a suitable topic to be reported. It is preferred that students report on different topics or different aspects of a characterization technique. And what is the duration of the report? 18 minutes lecture plus 2 minutes question and answer. So a total of 20 minutes per student. The students will be graded according to the following. For the completeness and quality or accuracy of information, that's 30% of the score. The use of adequate and updated sources, which are properly cited, 20% of the score. Organization and coherency, 25% of the score. And employs effective presentation techniques such as readable fonts, good contrast, high definition images, videos, and simulations if applicable. That's the remaining 25%. So total of 100%. And for the lineup, first, Mr. Donio will present his topic on TOF-SIMS, followed by Mr. Buenviaje, which is about FIB-SEM. And then last but not least, Mr. Hila.
Okay, so good afternoon, ma'am, and good afternoon, classmate. So may I present to you my chosen topic about the time of light secondary ion mass spectroscopy or TOF-SIMS. So my presentation outline includes what is SIMS, what is dynamic SIMS versus static SIMS, and I will going to talk a little bit about the limitation of SIMS and my main topic about TOF-SIMS and some applications of the characterization technique. So what is SIMS? So a SIMS is a destructive removal of material from sample by spattering and the analysis of the eject material by a mass analyzer. So this is the schematic diagram of the SIMS. I got this diagram from the book of Schroeder. And also SIMS measurements are well suited for semiconductor applications. So because SIMS is the matrix effects are minor and ion yields can be assumed to be linearly proportional to densities up to 1%. So why SIMS? So if you can see, as compared to some other characterization, TOF-SIMS, you can see the detection range and the analytical spot size. So top seams present good detection range, approximately 100 ppm to 100 ppb. So as you can see also in this diagram, you can see the dynamic seam. So increasing the probe current or the incident beam of the top seams, the result is the dynamic seams. So if you can see in the dynamic seams, even at low concentrations, the characterization can detect. So let's go to the generation of secondary ions. So if we have primary ions in this diagram, so this is the surface of the sample, and this is the primary ion beam, penetrates the surface, then energy loss through collision cascade. So in this surface, meron tayong collision cascade. Then primary ion implanted into solid. So the blue circle there. So na-implant yung primary ion natin. Then secondary particles including ions leave surface at low energy. So usually less than 1% of the total energy of the sputtering phenomena. Then escape depth of sputtered species only a few angstroms. Okay, so the collision, the important phenomena here in the generation of secondary ions is the sputtering phenomena, but it is a complicated phenomena according to the book of Paul van der Heijden. So if you want to study the details of the sputtering phenomena, you can check the book of Paul Heijden. Then, so what is the dynamic seams? So if you can see in this diagram, this is the secondary ions, then the primary ions. So if you can see on the surface, there is a crater created. So the intensity of one peak or one particular mass is recorded as a function of time as the sample is sputtered at higher sputter rate. So approximately 10 micrometer per hour, yielding a depth profile. So it can detect the elemental analysis. So it is an elemental analysis technique, and it has a high sensitivity impurity analysis of near surface 0 to 10 microns depth. So also for elemental analysis, and however, it has a minimal molecular information if we use the dynamic seams. And as I said a while ago, it has a high boom intensity, rapid material removal, and surface implanted with primary ion species to enhance ion yield. So this diagram shows using the dynamic seams. I got this diagram from the book of Schroeder. So this is a raw boron secondary ion signal versus sputtering time and boron profile for a boron implant into a silicon substrate. So as you can see, ion counts and time, you can see the profile, and also it converted to the density and depth. So if you can see, for depth profiling, the dynamic seams can be used. So also for static seams, sometimes yung static seams natin is usually the top seams. So if you can see, there is no, when we compare in the dynamic seams, wala tayong crater na nag-create. Okay, so this is the primary ion beams, secondary ion beams, then the topmost atomic layer. So for low incident ion beam current or low sputtering rate, about 0.1 nanometer per hour. Okay, and complete mass spectrum can be recorded for surface analysis of outer 0.5 nanometer or so. Also, chemical analysis of the surface. Through surface analysis, then molecular analysis and surface contamination can be detected. So, in the static SIMS, it has a very low primary ion beam intensity. So, primary ion beam, those primary ions impacting per square centimeter of sample surface must be very low such that ionization events have a higher probability of originating from a pristine undisturbed surface. Then it requires that less than 1% of the surface is disturbed or spattered. For example, your silicon has 10 to the 15 atoms per square centimeter. Then primary ion beam thus must be lesser than 10 to the 13 atoms per square centimeter. So we have also the limitation of conventional SIMS. Okay, so according to Schroeder, proper mass resolution is essential for an ambiguous SIM analysis. So for example, a SIMS mass charge spectrum for high purity silicon obtained with an oxygen, silicon, and isotopes polyatomic disilicon and trisilicon, as well as many molecular species involving oxygen. And also edge or wall effect. So instrumentation effect that complicates SIMS analysis. To avoid good depth resolution, it is important that only the signal from the flat bottom portion of the spattered crater must be analyzed. So the result is, that's why we have the top SIMS. So electrostatic or magnetic spectrometers depend on serial scanning of an electrostatic or magnetic field, requiring narrow slits for only those ions with the correct mass charge ratio to be transmitted. So this reduces the transmittance of the spectrometer substantially to values as low as 0.001%. So a SIMS approach without this limitation is time of flight SIMS or top SIMS. So in the top SIMS, instead of continuous sputtering by an ion beam, the incident beam consists of pulse ions from a liquid gallium gun with beam diameter as small as 0.3 micrometer. For pulse widths on the other nanoseconds, ions are spattered in brief bursts, and the time for these ions to travel to the detector is measured. So this is the schematic diagram of the top SIMS. So solid sample is bombarded with a pulse primary ion beam. So dito manggagaling yung primary ion beam natin. Then this is the sample. Then ions are emitted from outer layers, about 10 to 20 angstrom of the surface, and extracted. So yung mga secondary ions natin is magta-travel dito sa detector. This column magta-travel dito. Then their mass is measured by their time of flight to the detector. Okay, so yung flight nila dito is na-measure ng detector. Then nire-record as spectrum. Then this analysis cycle is repeated to generate the complete mass spectrum. Okay, so yung equating kinetic and potential energy, so this is the equation here. So mv square all over 2 is equal to Q all over B. Where B is your ion velocity, your big letter B is initial kinetic energy, your L is the length of flight tube. Ito yung flight tube, the length of the flight tube. Mass charge ratio, M all over Q, and T is equal to the flight time. So yung mga mas maliit na smaller ions is magta-travel faster. Okay, so magta-travel siya ng mas mabilis comparing to the higher mass secondary ions. So application of top SIMS. So top SIMS is a very highly sensitive mass spectroscopy which provides comprehensive elemental and molecular analysis of surface, thin layers, and interface with submicron lateral resolution. So top SIMS provides the profile of elements and or molecular ions as a function of depth. Also, mass spectral image of different species to yield surface reactivity maps. And also, mass spectrum of detailed information about the molecular structure of substrate. And also, in top SIMS, we can also do ion microscope. So, pwede nating i-image. A complete mass spectrum is first acquired, then after the acquisition, image can be generated using the peak of or groups of peaks of interest. So that is called the retrospective analysis. And also, this diagram shows the SIMS depth profile of a shallow silicon PN junction. Both arsenic and boron were measured with 3 keV cesium ions at 60 degrees incidence. And also, the profile of silicon carbide diode. So as you can see, the implanted, the diode is implanted with aluminum in this part, aluminum with certain depth. And also you can see the epitaxial growth of low N and also high N epitaxial growth, then the substrate. So you can see here in the x-axis the depth profile. So I have also, this journal shows the depth profiling of nanoparticles. However, it shows only the sputtering time. As you can see in the x-axis, yung lang pinakita niya is the sputtering time. So mas maganda sana kung meron siyang kinonvert na siya into, for example, micrometer or angstrom. So sputtering time lang yung pinakita. And also, I mentioned in previous slides that in top SIMS, pwede yung imaging. So this is an example of imaging using the top SIMS. So letter A, positive mode video clip image before sputtering, and B, after sputtering, and C, overlay color image, and D, scan raster area for zirconium oxide, europium, YB thin films. So while SIMS is ideally suited for solving a variety of problems by itself, so it is often used in combination with other analytical methods. So it is particularly complementary to X-ray photoelectron spectroscopy or XPS. So usually the strength of SIMS are often the weakness of XPS and vice versa. So kailangan talaga kung nag-top SIMS ka, gamitin mo din yung XPS para complementary sila. So this is my references. And thank you to everyone for listening.
Is a high vacuum important for SIMS?
Yes, ma'am. Top SIMS is a high vacuum instrument, ma'am. So ito ma'am, itong table 1 ma'am, comparison of static, top SIMS, and XPS. So andito yung property sa static top sinks, then yung XPS. Comparison ito ma'am. Bali, andito na rin yung weakness ng top sinks. So for example, ma'am, yung detection of all elements, nasa rank, mas mataas yung rank ng top sinks compared to XPS. So weakness niya is quantification according to this table, ma'am. So mas maganda yung XPS kung sa quantification. Yun po, ma'am.
It's a nice table. It shows the comparison between TOFSIMS and the XPS. The textbook mentions that the weakness is the destructive nature of the measurement. Right? So that means you might not be able to use the same surface of the sample for other characterization. You have to take into account that there are molecular species that have been ablated or removed already. Okay? So thank you.
Good afternoon. For my individual report 2, I will be presenting the topic about FIBSEM. So in particular, FIBSEM in this paper was applied to investigate the microstructure of coal. So this is the outline of my presentation. We will first discuss principles, parts, functions of FIB. Then going to the paper, we will deal with the problem statement, objectives, methodology, R&D, then summary, Q&A. So FIB, or focused ion beam, is a technique that employs a concentrated beam of ions to interact with the sample and generate images from the emitted secondary electrons. So if you will compare it to SEM, it has very similar principle, except that in FIB or in FIB, we make use of ions as incident beam. In SEM, we make use of electrons. So usually, FIB is not used as a standalone equipment or tool. It is usually connected to a SEM or TEM. So the use of FIB is actually more on the sample preparation, as you will see here. So this slide is just a illustration of the different material characterization. This is the same as Andrew's slide. Also here, you can see that the different depths, sampling volume, and profile depth of the different surface characterization method. So here, FIB is actually a tool that is connected to SEM or TM during sample preparation. So we have different kinds of FIB depending on the identity of the ion used. So we have gallium, we have plasma or xenon, and there's also a FIB that makes use of helium ions. So this is what I'm talking about. FIB is usually paired with SEM or TM, but in this presentation, I will be focusing on FIB-SEM that is used to combine the the power of the FIB as a sample preparation tool with the imaging capability of SEM. So in that way, you can have a precise machining of the sample, and you will be also able to image the sample. So it allows the users to fabricate complex designs or surface patterns using FIB, then image that site-specific modification using SEM. So this is an example of a FIB-SEM workstation. So the coupled FIB-SEM characterization. So common applications of FIB-SEM, semiconductors, electronics. It is also used in microbiology, medicine, fuel, and energy. So the governing principle, when the ion already hits the surface of the sample, is shown here. So as you can see, there can be many mechanisms that that could happen as the ion bombardment happens. So you can have the following: neutral atomic sputtering, incident ion backscattering, SE, secondary ion emission. So this is the one responsible for the imaging. Actually, the other emissions here could also be used for imaging. The others are important mechanisms in sample with regard to analysis of the sample composition or phases. So we will not deal each in detail each mechanism. So this our concern here is that FIB could induce such mechanisms. So basic parts of FIB, we have the ion source. So this is the source of the reservoir of ions used to bombard the sample. So in here, the ions are heated and excited to form a concentrated beam. We have the beam column, so contains the aperture, lenses, and deflector. So this is the part of FIB that is used to aim the beam on the sample. Then detector, like most devices, we have the detector to gather signals or to gather to detect electrons and convert them into signals, which can be used to construct images. So an important unique part of FIB is the GIS, or the gas injection system. This is used to emit, this is actually an auxiliary part only. The FIB can run without this, but it is a very useful addition to the capability of FIB. It is used to emit reactive gases to convert site-specific atoms into desired oxidation state, or inert gases to improve milling. So as you can see here, they have two functions. So you can use the GIS to chemically react the target area, or you can use inert gases to physically alter the surface of that target area through milling. So manipulators, again, this is also an supplementary part only. It allows complex controls of FIB. Usually, this is used in nanofabrication. So what are the functions of FIB? First and foremost, it is used for ion milling. Not just the ion milling of bulk samples, but it is a very precise ion milling. So it is the process of etching and removing material from the ions sample interaction volume precisely. So you can etch away certain shape or pattern depending on the purpose. So it is also called direct writing technique. FIB makes it possible to etch different geometries, including 3D shapes within the nano-range precision. So as you can see here, this is the GIS. Then you can etch away certain part through this GIS and form complex designs such as this one. So unlike traditional lithography, FIB also allows maskless creation of patterns. So it is more straightforward way of etching patterns or designs. So it is commonly driven by ion beam current and voltage, and also time of exposure exposure is a critical factor. So this is just an example of the impact of etching certain designs using FIB. It could affect mechanical properties. So another use of FIB is the opposite of milling is actually deposition. So again, the GIS is an important part. It allows the deposition of a material, certain material, on the site-specific target. So here, for example, the GIS could emit gas, typically organometallic, and it is done by it is the mechanism, governing mechanism is by chemical or vapor, physical vapor deposition. So in some applications, we want to convert or chemically react the target area to our desired oxidation state. So the GIS of FIB makes this possible, site-specific reactivity. So common reactive precursors that is used in sputtering, platinum, carbon, tungsten, and silica. So as I mentioned a while ago, if the application does not intend to chemically react the target site, GIS can be also loaded with inert gases to physically alter the surface by using inert gases. So I've come across this paper. It is a recent paper, just last January 2022. It is a paper that tackles the use of coal as a use of coal as a electronic product. So as we all know, there is a global advocacy to abolish coal powered energy sources and replace with renewable and more sustainable energy source. So the question now is, where does coal come? What will be the future use of coal? So there are now studies tackling this, and the innovation here is that coal can be used to convert can be converted to electronic products. So here it is CO2 laser was used to alter the coal composition and structure to be used as uh, an electronic device. So, but the paper, this is not the paper that I'll be discussing. What piqued my interest is that how can you use FIB to deal with coal? So the important aspect is that to be able to make use of coal, aside from the energy, its function as an energy source, it's important to analyze the microstructure. So in that way, that could be a starting point to explore the other possibilities of using coal aside from as an energy source. So FIBSEM is a great tool to do this. It can be used to analyze in detail the 3D, the structure of coal samples. So in this paper, this is the actual paper that I'll be reporting. In here, the FIBSEM is used as a tool to reconstruct the 3D structure of lignite, which is a type of coal. So solid type fossil fuels like coal originate from organic matter that transform into deposits known as lignite. So these are the types of lignite. So there could be 5 types depending on the composition of the sample. It could be rich in silytic, it could be rich in detritic, or it could be a mixture. So the problem statement of the paper is that coal has a poor energy efficiency. So meaning for a given mass of coal, it has the least efficiency in terms of energy conversion compared to other sources such as oil, natural gas, solar, etc. So to be able to dig deeper, it is imperative to understand why is it inefficient in terms of energy conversion. It is because there is a lacking in terms of structural investigation. As we all know, coal is usually being handled in bulk. So as I explored the available journals, there are very few studies dealing with understanding the microstructures of coal and its relationship with energy efficiency. So in here, the gap being addressed by the paper is the lack of an accurate method to structurally assess the microstructure of coal. So there is an existing method, the fluid invasion method, but it has limitations. First, it is not capable of building a sophisticated or detailed tree model. The geometric model is usually oversimplified. Also, it is not capable of representing the internal cavities. So fluid invasion method is actually done by first injecting doses of fluid, then example is methane, nitrogen, carbon dioxide. Then the emission of these gases are used to evaluate the sizes and dimensions of the mesopore and micropore structures. So that's what is mentioned in the paper. I will not be discussing that in detail. So these are the 2 limitations of that method. So the objective of the paper is to use cryo-fib-sem tomography to analyze the microstructure of lignite samples and to reconstruct its 3D model. So methodology is in 3 stages. First, sample preparation. The cryo here is actually another advantage of fib-sem. There is already a fib-sem equipment that is capable of analyzing the sample in cryogenic state. So meaning you can preserve the internal humidity of the coal sample without actually that could affect greatly the structural integrity. In fluid invasion, that's also a limitation. Usually, the injection of fluid already affects the structure. So what you will be getting from the model is not an accurate picture of the structure of the coal. But in cryogenic fib-sem, the machine is capable of preserving the actual humidity of the internal structure of the coal sample. Then this is the fib-sem used, and the image processing. In image processing, Aviso is the software used. So methodology, a 2-kilogram coal sample was obtained from this place. It's a mining field in Poland, located 75 meters below sea level. So this is they have included a vicinity map of the sample extraction. So this is where the sample was extracted. So the paper was pretty straightforward. It's just they obtained SEM samples. They have used FIB to etch the lignite samples, obtain SEM pictures, as you can see here, then replicate that through various slices of the sample. The FIB was used to slice or to etch slices, the sample into slices, obtain the same image per slice, then tailor those images to create a 3D model. So it is important here. Okay, I will move to the next slide. So an important consideration here is the phases. So there's actually two phases, as I mentioned a while ago. Lignite can be composed of detritic or silytic coal. So I'm not an expert in coal types. So according to the paper, these are the visual appearances of a detritic coal and a silytic coal. So what they did is that they obtained the same image, identify the faces by segmentation, then identify the faces. So in here, this is the silytic coal. Then this is the detritic coal, this part. Then transform them into a recognizable image that can be used, that can be fed into the software. So I'll not be dealing with the details of using the software, but using this technique, using the slices of the same images of the slices of the coal sample and feeding them into the software, the authors were able to reconstruct the 3D image of the coal sample, a section of the coal sample. So they started with this one, and they were able to recreate. So these are the parameters used in reconstructing the 3D model in terms of image properties: pixel size, pixel count, and picture distance. So in summary, we were able to have a new perspective about FIB-SEM, that it can be used to recreate 3D models of complex microstructures using FIB-SEM, the capabilities of FIB-SEM, and software, modeling software. So aside from in here, the example was coal sample lignite, but it could be extended to various applications. Mostly in the journals I've encountered are focused on medicine. It is used to reconstruct tissues using FIB-SEM images of cell samples. So these are the references, and that's all for me. Thank you for listening. Are there questions?
So the topic is still related to electronics and semiconductors. What is the diameter of a gallium beam?
I think I have not included that here.
It's okay. So as stated in our reference book, the diameter of a gallium beam is 10 nanometers.
Then.
And also these ion beams, they are also rastered, right? On the portion of the sample.
Yes, correct.
So similar to how the SEM electrons operate, the ions are rastered over a given portion of a sample. So what is meant by raster scan?
Bombardment of ions
Okay.
using a in the form of concentrated beam.
So recall in your SEM, you have these rectangular patterns with parallel scanning lines, and the electrons will follow those parallel scanning lines. So in the FIB, the ions will also follow the parallel scanning lines. Okay, so that's the first part of individual reports number 2 on physical and chemical characterization.